Like basically, wouldn't you get like 2x to the negative 1 plus?
So bring this up.
Yeah.
That algebraically would be okay, but me personally, I would just split this into two fractions like this. Like to me, this makes the most cleanest sense to me. Am I allowed to do that? 2 terms over 1, I can split it. Now this, I can handle that by itself now because that's really like 1 over 2 times 1 over x. That's what that is. And then over here, if I cancel one of the x's, that's really like a 1/2, right? 1/2. And then x squared over x is x. And then do you see that I can do each of those individually now? Right? That 1/2 comes for the ride. Antiderivative 1 over x is natural log. And then 1/2 comes for the ride. What's the antiderivative of x? 1/2 x squared. Do you see how that can be done? That can be done. But if we flip it, we can't do it. All right? Questions there? We're still here stuck, but I just wanted to show you that if I just make a quick change, we're okay. Right? Yes?
Is there like a sine or a cosine that we can do with this, though? It looks like a sine or cosine.
I think it's a 10.
Or a tan.
Inverse?
Yeah.
Inverse, well, that's what we were saying in the beginning. Like if the 2x wasn't there, right? If that was 1, we'd be done. We'd just say the antiderivative of this is arctangent of x. But there is a 2x here, and we can't get rid of it. Even if there was a 2 here, right? Even if it was 2, I could handle that. Because then I could pull the 2 out and do them. There I can do them separately because 2 is a constant. I could do that.
Can we not multiply 1 over 1 plus x squared?
By?
By 2x to separate it? And then, no, we're just
We did that, didn't we? We did that. We wrote 2x separated and then 1 over 1 plus x squared. We did them separate.
The problem was that they were multiplying by each other.
They were multiplying, and when it comes to antiderivatives, you are not allowed to take the antiderivative of 2 factors individually. You can't.
I'm not allowed to take the antiderivative of 2 factors individually.
Let me give you all a different example, okay? Just so everyone's clear on this. Let's say I have x times cosine x dx. I'm trying to find the antiderivative of this, okay? Let's say I'm trying, all right? And let me put a 2x here just to make this a little bit cleaner. The question is, can I do this? Can I say that that's 2x times cosine x dx, take the antiderivative of that one, which is x squared, take the antiderivative of that one, which is sine x. You all following me?
Yeah.
The question is that okay?
No.
Plus c. How can you convince me that this is not okay?
Well, because you're multiplying. You have to do the product rule.
Convince me though.
But then if you try to do it backwards,
Okay, so now check your answer. Check your answer. If I take derivative of this, I better get that, right?
Yeah.
Okay, so how do you take derivative of this? Product rule. Okay, starting here, what do you get? Derivative of that is 2x times, okay, plus now derivative of this, cosine x times x squared. Is that this? No, so it doesn't work. You see?
Yeah.
It's unfortunate. I mean, yeah. This is why back even in Cal 1, if the product rule was different, calculus would be much easier, right? If the product rule said, hey, just take derivative of each one separately, man, it'd be nice. But that's just not the way it is. Yes?
So what comes after this is use substitution, right?
That's what we're about to do.
Yeah, so does that come from like conceptually, does that literally come from thinking outside the box and using dx like as a part of the equation rather than thinking of that as like just part of the question?
I'm not sure, like historically, when humans like figured out, let's try this, like what the motivation was. But it was a point in time where, you know, we got stuck, right? So people tried different things, and that this method kind of came up as something that works, right? Not in every case. This is not the magic pill, okay? What we're about to do is not like going to solve all of our problems, but for certain problems, it works, okay? So watch what I'm doing, all right? If you've never seen this, okay, show of hands now for this. How many of you have seen U substitution? Well, that's good. Okay, a lot of you. So I'm still going to teach it like you never had, like you've never seen it, all right?
I think we started in college algebra. Yeah.
Cal 1? Oh, no. That's U sub in college. U sub is like a generic word for just any time you take something and replace it with U. But in Cal 2, it's a specific type of finding antiderivatives. Okay, so here's what I'm going to do. Let me explain, because it's taught many different ways, and there's going to be little differences in my notation than the way someone else might have done it. I'm aware of that, so I hope you didn't learn it too much where I'm going to confuse you with my method. So what I'm doing is I'm looking at this. I'm looking at the integrand, all right? And what I'm looking for are two things. I'm looking for something in there. I don't even know what it is yet, but it's something. And I'm hoping that whatever that something is, whatever this something is that I'm looking for, I'm hoping that I'm also going to see somewhere in the problem the derivative of the something. Okay? I need to see both of those, okay? So these are my eyes, right? And so I'm looking to see both of those things in the problem. Somewhere in the problem, I'm looking for something, and then also the derivative of that something should be appearing to me as well. However, there's a little catch. This derivative right here that you see must be in the numerator, and it can't be trapped. And what I mean by trapped is that it can't be underneath a root, it can't be in a parenthesis being squared, it has to be isolated. So, must be in the numerator, can't be trapped, cannot be inside of a sine function, then it would be trapped, okay? Also, there's one more thing. It can be off by a constant. You're going to have to let me work through a few of these for you to understand all of this. Now, for this first example, I made everything beautiful. Everything works perfectly. All right? So you're looking for something, and then you're hoping to also see its derivative there as well. So do y'all see the something I'm talking about? Yes. What is it? The whole bottom? 1 plus x squared, right? What's the derivative of that? 2x. That's the top, right? Now, hold on. You said 1 plus x squared. Could I have done just x squared? Sure. What's the derivative of x squared? 2x. So that would have worked as well, right? The thing about this technique of substitution is that you want to get as much as you can, like grab as much as you can without grabbing too much. All right, so x squared, although it would work, because 1 plus x squared also works, I'm going to go with the 1 plus x squared. Okay? I'll do another example after this where I change it just slightly, and we'll still try and play that game of not grabbing too much. See, all right. All right, so you see the something? Yep. That's my something. And that is the derivative of the something, right? Right up there. Is that derivative in the numerator? Yes. Is it trapped? Is it under a root? Is it inside of a trig function? No, right? It's just sitting there, 2x, nice and pretty up there. All right. It can be off by a constant, meaning this could have been a 5x, and we would have been okay. Doesn't have to be exactly 2x. It just needs to be some number in front of x. Off by a constant would be okay. If it was just x, we'd be okay. All right? So once we identify it, here's the technique. I'm going to make the substitution, just like we would do in college algebra. So I'm going to let u be equal to the something, which was the 1 plus x squared. Okay? Then I'm going to differentiate this implicitly with respect to x. So I take the derivative of u with respect to x, and then that gives us 2x on this side. The next thing I'm going to do is get du by itself by multiplying both sides of this by dx. All right, that's the setup for the problem. You write down this something, you take its derivative with respect to x, and you multiply both sides by dx. Now I come back to the problem. I'm going to rewrite it because I wrote too much crap all over the place. I'm going to rewrite this problem, but watch the way I rewrite it. I'm going to slide that 2x off to the side. That 2x that was up there, I'm just going to slide it over to the side because that's the same as 2x over 1, right? And so that 2x can live up there or it can live off on its own. I'm going to move it off on its own for one particular reason. And that is so I can play this little game where I try and match things up. Where I try and like match things over here to things over there. So how about this first? Everyone see that the 1 plus x squared, that's what u is, right? That's u. And then we have the 2x dx, including the dx. 2x dx matches that exactly, doesn't it? Yes?
Just so I get this straight, so you can be like anywhere in the equation, like it can be trapped, but the derivative you can't.
That's right. Whatever u is can be trapped, but the derivative of it cannot. Yeah. Any other questions? I'm not done. I'm just setting it up, right? So what I do now, once I figure out what I'm going to, what matches with what, the goal is to now rewrite this integral, but in terms of u instead of x. So I want u's in here instead of x's. So all x's have to disappear somehow, and everything in the integral should now have u's in it. So we're changing the variable, right? We're making a substitution. We're substituting out x for a new variable u. So this now becomes the antiderivative 1 over, well, this is what? U. And then times this is du. And now this should be a simple problem for us because we know what the antiderivative of 1 over x is, right? If x was our variable. What's the antiderivative of 1 over x? Natural log, right? Well, this is the same problem, but just we're using u instead of x. So the antiderivative of this would be natural log of absolute value of u plus c, right? This means find the antiderivative of this thing right here, treating u like the variable. Well, the antiderivative of this is this, right? And then because it's an antiderivative, I always have to put plus c. We're not done. Because our answer is in terms of u, and our original problem was in terms of x. So we need our final answer to be in terms of x. So I'm going to replace my u now with 1 plus x squared. Yes?
What happens to the du when you took the...
Okay, so everyone always asks, where did that du go? The du only keeps track of your variable. So when you're looking at this, this means antiderivative, right? Antiderivative of what? That. What's the variable? That. So the antiderivative of this is just that right there, right? The plus c is because we always throw a plus c on antiderivatives. So this doesn't really go anywhere. It's not part, we're not actually trying to find the antiderivative of this. You can ignore it and just do that. It's a weird thing. I always tell my students, if you're really having trouble with what happens to this, just make it be the plus c. Like that's what happens to the du, it becomes the plus c. Even though that's not at all what happens, it'll help you remember the plus c.
It's just to keep like yourself on track, I guess?
It keeps track of the variable.
Okay.
Yes.
I guess like a good way to think about it is that what's that symbol called again? The
Integral?
Yeah, it's like that and the du, like they're used up to take the antiderivative.
Yeah, exactly. They're kind of, this one and this one together are telling you what to do to that.
Yeah, and then like after that, there's like
After that, you've done it, right? So it's like the prime mark when you take a derivative, the prime. After you actually take derivative, there's no more prime mark. What happened to the prime? Well, you did the operation, right? Okay, I'm going to do the same problem. I have a little bit of time. I'm going to do the same problem. I'm going to change it just slightly. 2x over square root of 1 plus x squared dx. Almost the same problem, isn't it? Almost the same problem. You want to rule out that there's nothing else we can do to this. Like there's no like, hey, this is just blah, or we just split it up into two pieces and we're happy, right? So once we've kind of conceded to the idea that we need something else, right? We'll try the u sub. So we're looking for something in its derivative, something in its derivative. So yeah, go ahead. No, don't.
I guess how much of an effort should we make into trying to see if we can avoid doing the substitution, or should we just give up and concede to the substitution already?
Yeah, I think it's going to come with practice and time, where you know when it is you need to start going down this certain road. And your question is actually what makes the Cal 2 extremely difficult after exam 1 when you get to exam 2. And that's that you don't really know what you're supposed to do because there's 4 or 5 different things you could do, right? And so you're sitting there, and that really is only going to you'll become comfortable with it after you've done a lot of problems. So it's going to just be like an evolution for you on how long that takes for you to like move on to the next thing. All right, so here, or you could just look at this and just right off the bat, you're like, holy shit, u du. Like, here's u, there's its derivative. Like, I'm going there right now, you know? You don't have to do other stuff. I see it. There's its derivative, right? So I'm going to start with, now hold on. Should we try and go for more? Should we try and go for more than just the 1 plus x squared? Should we try to grab, don't write this down, should we try and grab the square root as well?
No, because it's not the same derivative.
Well, okay, so if that's my u, does everyone see the u right there? Okay, go ahead.
I want to clarify, so that it doesn't matter if the x squared is trapped in a
Nope. The something that you're looking for can be anywhere. The derivative can't be trapped. Okay, the derivative can't be trapped. See, this something here is trapped. But why am I not going to use that something right there? What's the derivative of this? So you have to do chain rule here, don't you? So derivative of the square root of something is 1 over 2 square roots of that something times the derivative of what's inside, 2x, the 2's cancel, and you get x over square root of 1 plus x squared, right? That's what you get?
So the denominator is trapped.
Well, you've already called this u, haven't you? You've already called, this was our u down here. That's what u is. So the only thing that's left is that, right? That's already u. So if that's u, the derivative is that, right? Do you see that derivative here? No, right? Like that over there is way more than what I have left, isn't it? You're not allowed to look at this again because that was already u, you see? So it's this like fine line where it's like you want to go get a u, but you don't want to grab so much that the du isn't there. The derivative of it isn't there.
You just keep doing it and practicing with it.
Practice, repetition. All right, so here we go. So I'm going to go back to this one. We already established that the derivative of that with respect to x is 2x, and then I multiply both sides by dx. And then I'm going to go back over here, and I'm just going to play that game again where I just move things around. Is this going to be the exact same answer as the previous one? No, why not?
You're not going to have natural.
Yeah, when I replace this thing with u, it's no longer going to be 1 over u, it's going to be 1 over square root of u, and that has a different antiderivative than 1 over u. So it's going to be different, yes?
Why can't the u just be like x squared?
It could have been x squared, it could have. But if you do that, you're going to add an extra step. You're going to have to do a second substitution because you'll be able to replace this with u, right? And this will become 1 plus u square root instead of down here, which is just going to be square root of u by itself, not 1 plus u. So always, when you're grabbing whatever u is, try and just look like one step further. Can you grab a little bit more? If you can, great, do it. If you can't, stick with what you've got. All right, can I rewrite?
Yes.
Okay, so this becomes integral 1 over square root of this right here. Do I need to do all this? I know a lot of you said you've done this already, so There, that's that. And then this right here is going to be this right there, right? So 1 over square root of u, and then the rest of it is du. Do we have a formula for that? Because we should be able to take the antiderivative of that.
No, because that would be like what, natural log of absolute value, square root of something.
Yeah, that's if the natural log only works if this was 1 over u, though, right? So
U to the 1/2, you bring it up.
exactly, we're gonna rewrite this. We're gonna rewrite this as u to the half on the bottom. Square root means u to the half, and then I'm gonna bring it up as u to the negative half, and then I'm gonna use the power rule, right? I know how to find the antiderivative of my variable to a power, right? So this will be, okay, I'm going to take that u, I'm going to add 1 to this power. What happens if you add 1 to that power? You get a half. And what number do I need to multiply by out here? 1 over a half, which will become 2, right? So this is my power rule. You all comfortable with that? I'm using that x to the n rule, except instead of x, we have u. So I'm adding 1 to the power, doing 1 over, this is n plus 1 down here. So adding 1 to the power, plus c. 1 over a half is 2. This really means square root of what? So this means square root u, but u was 1 plus x squared. And again, the good news there is that you could check your answer, couldn't you? Like you could actually check to see if that works by taking the derivative.
You check to see if it works by just taking the derivative?
Yep, just take derivative. And as long as you know how to do the chain rule and all those rules properly, you should be able to know if you got it right. All right, so do you have the basic understanding? Like, I mean, you have to do more problems, but the basic idea behind substitution, you're looking for something, looking for its derivative, you can make sure it's a numerator off by a constant. Yes?
How fast should we be able to do this?
Well, right now,
By the time we take the test?
I don't know. This particular problem, I don't know. A couple of minutes? Yeah. Was there?
I was gonna say, so is it, you only said you have to like turn and grab, so is it better, if you have to grab exactly, is it better to try and grab too little or too much first, or how is?
You're just going to grab as much as you can without going too much. It's always as much as you can without too much. Because if you don't grab enough initially, you're going to have to do the process repeatedly. You're going to have to do it over. I mean, do it again, do a different substitution, second substitution. So it's better to just grab as much as you can. Yes?
Are there equations where like we have to do a second substitution?
Yes. Yes, but not here, not yet. When we get to integration by parts, there'll be problems where we have to do a u sub first, then integration by parts, and then we might have to do a u sub again.
So that's why you said you have to grasp step 1 before.
Yeah, you just have to be comfortable with this idea. Yes?
Will it always be like a fraction?
Nope. It won't always be a fraction.
Is there a list of questions that are specifically like only solvable by u substitution?
Well, they're in the book, right? Section 5.5 are all u substitution problems, which is where your homework's going to come from. All right. How about this one? I'll try and give you one that's not a fraction, just to have. How about this? X secant x squared plus 1 tangent x squared plus 1. I'm trying to keep this pretty straightforward right now. I know it looks terrible, but this would be considered to be pretty straightforward.
So your derivative could be off by a constant, so you have to throw 1/2 out front.
Yeah, so we have, what's your u going to be here? Do y'all see the u? X squared plus 1. Why? If you let u be x squared plus 1, the derivative of that is what?
2x.
2x? You have an x, don't you? Is it in the numerator? Well, we don't really have a denominator. Well, we do. There's 1 in the denominator if you want, right? but that's in the numerator, and it's off by a constant, isn't it? So I'm going to start writing some things down. If I let u be x squared plus 1, the derivative of that with respect to x is 2x, right? Right?
Yeah.
I don't have 2x, I have x, right? So it's off by a constant. I said that's okay to be off by a constant. We still all right? Watch what I do, because again, the way people are taught this is different depending on the instructor. So I'm going to show you the way I do it. If you are super comfortable with this already, do it your own way. I always do this, multiply both sides by dx. I do that every single time. And then I play this game where I try and make this match up with what's over there. So I'm going to rewrite this as secant x squared plus 1 tangent x squared plus 1. See that x that was there? I peel it off to the back side as x dx. Because this is multiplication, I can move that x all the way to the back next to the dx, right? So I see that right here, I have x dx, right? That matches up exactly with this right here. The problem is I don't have the 2, right? The 2 is off. So what I do is I take this equation, because that's a little equation, right? A little tiny equation. I'm going to multiply both sides by a half. And that will kill the 2 off over here. If you want, you can say divide by 2. So I'm going to do half of du is equal to x dx. And now they match exactly, right? This matches exactly with that. And then, pardon? Go ahead. I have x dx here, right? Here I had 2x dx. I just want x dx, so I got rid of the 2 by dividing both sides by 2. Now x dx matches that exactly, right? Also, everywhere I see x squared plus 1, that's going to be replaced with u, right? So what does my new integral look like if I do my substitution here? I have secant u, tangent u, and then that gets replaced with half of du. Half of du, right? Now, what is it about constants that are attached to functions? You can always move them out front and just kind of bring them with you, right? As long as the constant is attached to the function, you can do that. So this line could become, I could put the 1/2 right here inside, or I can even take it outside as a multiplication, which is what I will normally do in this class. Take constants outside the integral sign. Secant u, tangent u. I'm not going to write the parentheses around the u anymore. Du.
Wait, is there a reason why we take constants outside of integral?
Just because they're just getting our way, and just bring them out. Just like when you're taking a derivative, if you have a constant, it's just going to come with you the whole time. So here I'm just going to drag it along with us in the front. Whatever this answer is, I'm just going to multiply it times a half. Any questions on where we are right now? Do you know the antiderivative of that?
Yes.
Secant u. Secant u. That again is from Cal 1. The derivative of secant of x is secant x tangent x. So here, this becomes 1/2. No more integral sign, right? Secant u plus c. Right? That's our answer. No more integral sign, right? Where did the du go, if you want? It's the plus c, right? Okay. We're almost done. We're almost done. Except we have to replace u with what u was, right? Which was x squared plus 1. Be real careful that x squared plus 1 must be in parentheses plus c. And then you could check your answer if you want, but it works. I've got 5 minutes. Let me see if I can cram one more in here. All right, how about this one? This is just to give you a glimpse into that things aren't always as simple as, oh, I see something and its derivative, right? You want to make the u 1 plus x? If you want. I mean, I'll do anything you want me to do. As long as it's algebraically legal, I'll do it, right?
Make it X.
So one thing I'll say, on u substitution, which is what we're doing right now, never let u be x. Only because if you do that, all you're going to wind up doing at the end is rewriting the whole problem, and it'll just be u's here instead of x's. And it won't get you anywhere. So never let u be x, just x. You can do something else, though. I mean, I'm up to anything other than that. Let me ask you, do you see something in its derivative? 1 plus x, okay, if you're seeing this, if this is your something, what's the derivative of that? 1, do you see 1 somewhere up top? Yes? Okay, so that is, I mean, that's falling within what we've said, right? Something is derivative, yes?
Can you foil that?
Foil, expand, you could multiply that out, yeah, you could. That's legal. But I'm asking, do you see something in its derivative, just as it appears right now?
Would you rather foil u or would you rather foil?
I'm not foiling it. That foil implies that there's two binomials, and that we're foiling. So this is actually expanding. You're multiplying this through, so that's called expansion. I just don't want to use the wrong words, if you know what I mean. So this is expanding, or just distributing, or you could just say multiplying through. So what was your question? Do a what?
Oh, I was actually asking the guy who asked.
Oh.
Because it's like,
Oh, okay. I thought you were asking me.
because it's like you can make it a lot easier instead of the square root x times 1 plus that, figure it out. You could just substitute with u. Only is one. I don't know what you call it. Translocation.
The only thing that anyone has said is 1 plus x. The derivative of that is 1. And we all do agree that that is there, right? There's a 1 there. So that is, I guess, a legitimate approach that we could try. Nobody said square root of x. What's the derivative of the square root of x? 1 over 2 root x, right? I talked to you all about that we should probably get to a point where we are comfortable with this idea, right? So if I let u be this, the derivative of that is this, and I don't see that anywhere, do you? Right, because you've already used, this is going to be your u, right? That's going to be your u. And then if that's your u, the derivative of it, I don't see that over here, right?
So we
Kind of
see
is,
two.
but does it have to be in the numerator?
It has to be in the numerator, yeah,
And that's not a constant, so.
yeah.
Seems like
So.
x plus 1 is the only thing that would
Seems like x plus 1 is the only thing we can do, and I only got like 30 seconds. Let's try it. U is